Welcome, guys. In this video, we are going to study absolute maxima and minima problems. In section 4.2 on relative extrema points, we studied points where our function has largest or smallest value in some vicinity of a point. Now we are going to extend that concept and we'll find such points where our function has smallest or largest value in the whole open or closed interval. So consider an interval in the domain of a function f and a point x0 in that interval. We say that function f has an absolute maximum at x0 if values of function at all points x in that interval are less or equal than the value of function at that point x0. And we say that function f has an absolute minimum at x0 if values of function at point x for all x in the interval are greater or equal than the value of function at that point x0. We say that function f has an absolute extreme at x0 if it has either absolute minimum or absolute maximum at that point. Existence of absolute extrema points is not always guaranteed. Let's take a look at the following graphs. In the first graph, we can see that our function increases without bound as x goes to minus and plus infinity. In this case, we have an absolute minimum, but no absolute maximum on interval from minus infinity to plus infinity. In this case, this looks like a graph of function y is equal to x. Our function decreases without bound when x goes to minus infinity, and our function increases without bound as x goes to plus infinity. This function has no absolute extrema at all on interval from minus infinity to plus infinity. In this case, we can see that our function has both absolute minimum and maximum points on interval from minus infinity to plus infinity. So here is our absolute maximum point. Those 2 points here, if they have the same value of function, they correspond to absolute minimum points. In this case, our function on open interval from a to b has now absolute extrema. In that closed interval from a to b, this function has both absolute maximum and absolute minimum. So absolute minimum is at point A, absolute maximum is here at point x is equal to b. This function here helps us with the existence of absolute extrema of a function in a closed interval, known as extreme value theorem. If a function f is continuous on a finite closed interval from a to b, then f has both an absolute maximum and absolute minimum on that closed interval. Also, if f has an absolute extrema inside of that closed interval from a to b, then absolute extrema points must occur either at a closed interval from a to b or at an endpoints. And this theorem here helps us to find absolute extrema points inside of open interval from a to b. If f has an absolute extremum on an open interval from a to b, then it must occur at a critical point of f. So it must occur at either stationary points or points where our function is not differentiable. This theorem here is also valid for infinite open intervals. So intervals of the type from minus infinity to plus infinity, from a to plus infinity, and from minus infinity to b. So procedure for finding the absolute extrema of a continuous function f on a finite closed interval then is following. So we know that this function will have its absolute extrema points either at an endpoints or inside of this open interval from a to b. And from theorem 4.43, we know that if this function has absolute extrema inside of this open interval, then it must occur at critical points. So our first step is check inside of this open interval by studying its critical points. Then we are going to evaluate, and we also know that this function might have its absolute extremal points at the endpoints of that interval. So we need to check these endpoints. So we are going to evaluate the value of our function at those endpoints and at these critical points that we found in step number 1. And then we are going to compare these values between themselves, and the largest value in step 2 is going to be absolute maximum of this function on that closed interval, and the smallest value is going to be an absolute minimum. So here we can see several cases. In first case, we see that there are no critical points of function f in that open interval from A to B. So absolute extrema points are happening at endpoints, and at point A we have absolute minimum, at point B we have absolute maximum. At this function here, we see that it is continuous, so it must have its absolute extrema inside of that closed interval from A to B. So we see that this function has 2 stationary points, and what we are going to do, we are going to evaluate the value of function at those endpoints, and we are going to compare the value to the value of function at these stationary points. And we see that absolute maximum is happening at this point x0, and absolute minimum happening somewhere at this point here. In this last case, we see that our function is continuous again on interval from A to B, and it has a stationary point somewhere here, and it also has a critical point at x0 where it's not differentiable, so corner point here. Again, we are going to evaluate our function at an endpoints, and then we are going to evaluate our function at those critical points. And then we see that our absolute minimum is happening at this point, at this stationary point here, and absolute maximum is at this critical point x0. All right, let's solve the following problem. Let's find absolute extremal points of the following function on this closed interval. So this is a polynomial, so it is continuous, meaning that it will have absolute extrema inside extremal points inside of this closed interval. First of all, let's find critical points. Let's differentiate our function. So derivative is equal to 6x squared minus 30x plus 36. Let's factor out 6. So we'll end up with 6x squared minus 5x plus 6. So the roots are then 2 and 3. 6x minus 2, x minus 3. All right. Now we are going, so our critical points are stationary points, in fact, are x is equal to 3 and x is equal to 2. And our endpoints are x is equal to 1 and x is equal to 5. So we are going to evaluate the value of our function at n endpoints. At point 1, the value of function is equal to 23. At point 5, the value of our function is equal to 55. Then we are going to evaluate the value of our function at those critical points at 2 and 3. So at point 2, it's equal to 28. At point 3, the value of our function is equal to 27. Now we are going to find the largest and smallest values out of this. The smallest value here is equal to 23. So at x is equal to 1, we have absolute minimum of this function on that closed interval from 1 to 5. And at point for x is equal to 5, we have absolute maximum. Existence of absolute extrema for a function on infinite intervals is not guaranteed, but we can study the end behavior of our function to find whether this function has absolute extrema or not. So for instance, if we have the following continuous function, and if its end behavior is that it's going to increase without bounds when x goes to minus or plus infinity, then our function will not have absolute maximum, but it will have absolute minimum on interval from minus infinity to plus infinity. In case when our function decreases without bounds, when x goes to minus infinity or plus infinity, then our function will have no absolute minimum, but will have absolute maximum. In case when function is going to decrease without bounds and increase when x goes to minus infinity and increase without bounds when x goes to plus infinity, then as we can see from this graph here, it suggests us that function will not have absolute extrema, neither absolute maximum and absolute minimum. In case when our function is going to increase without bounds when x goes to minus infinity and decrease without bounds when x goes to plus infinity, our function will also have no absolute extrema. What can you say about the existence of absolute extrema on interval from minus infinity to plus infinity for polynomials? For polynomials, the end behavior is the same as of the leading term. And our leading term for polynomials might be odd degree or even degree. Let's say that here we have odd degree polynomial. So leading term has odd degree. And second case, let's assume that our leading term is of even power. Then if we take limit when x goes to plus infinity of odd degree polynomial, then this term here is this is equal to limit x goes to plus infinity of a leading term. Okay, and based on sign of an on the leading coefficient, then if it is negative, then that limit is going to be equal to minus infinity, and if it's positive, it's going to be equal to plus infinity. And if we take a limit of odd degree polynomial when x goes to minus infinity, let's compare these two for cases when an is positive. So that limit will be equal to plus infinity, and this limit here will be equal to minus infinity then, since this will go to minus infinity, meaning that our function, our polynomial, will not have absolute extrema. And in case when this coefficient is negative, the same is going to happen. This limit will go to minus infinity, and that limit will go to plus infinity, meaning again that our function will have our polynomial will have no absolute extrema. In case when we have a polynomial with a leading term that has even degree, then this limit is equal to, in case when the leading coefficient is positive, then this limit is equal to plus infinity, and limit when x goes to minus infinity of an x to the power 2n. If an is positive, then this limit will also again go to plus infinity, since this term will go to plus infinity, meaning that our function increases without bound when x goes to minus or plus infinity. So this function will not have absolute maximum, but will have an absolute minimum. In case when a leading term coefficient has negative sign,
then that limit will go to minus infinity, since this term will go to plus infinity, and this term will also go to minus infinity, meaning that our polynomial will decrease without bounds when x goes to minus or plus infinity. So our polynomial will have no absolute minimum, but will have absolute maximum. And we can then find absolute, the location of absolute maximum in this case, or absolute minimum in that case, by finding stationary points. Let's determine by inspection whether the following polynomial has any absolute extrema. If so, find them and state where they occur. So this polynomial has leading term with even degree, and leading coefficient is also positive, meaning that it's going to increase without bounds when x goes to plus and minus infinity, meaning that this polynomial has no absolute maximum, but it is going to have absolute minimum. To find absolute minimum, then we are going to differentiate our polynomial. So f prime is already found here. We are going to find critical points, stationary points in case with polynomials. So we have two stationary points, x is equal to 0 and x is equal to minus 1. So we are going to compare values of our function at these two stationary points, this at 0 and minus 1. So we find that our polynomial has absolute minimum at x is equal to minus 1. And we can confirm that by graph. Here are our two stationary points. At point 0, our function is equal to 0. At point minus 1, it's equal to minus 1. So this polynomial has absolute minimum that is equal to minus 1 at point x is equal to minus 1, an interval from minus infinity to plus infinity. Existence of absolute extrema of a continuous function on an open interval is not guaranteed, but we can study its behavior near endpoints of that interval to determine whether this function has absolute extrema or not. So let's take a look at the following case. In this case, our function is going to increase without bounds when we approach endpoints of that interval. So since our function is increasing without bounds, this function will not have absolute maximum, but will have an absolute minimum. And we can find that absolute minimum by finding critical points inside of this open interval. Right, in this case, our function is decreasing without bounds when we are approaching these vertical asymptotes. And in that case, the function will have no absolute minimum, but will have absolute maximum. All right, in these two cases, our function, the sign of limit when we are approaching endpoints of that interval are different, meaning that our function in this case is decreasing without bounds on left-hand point and increasing without bounds on right-hand point. Both of these cases, and this case is similar, both of these cases, function will have no absolute extrema. Let's determine whether the following function 1 over x squared minus x has any absolute extrema on open interval from 0 to 1. If so, find them and state whether they occur. So we are going to find limits. We are going to study the behavior of our function when it's approaching to endpoints of that open interval. So we are going to take limit when x is approaching to 0, left point of that interval from the right. And then we are going to find limit when x is approaching to right endpoint of that interval from the left. Both of these limits are equal to minus infinity, so our function is decreasing without bounds when we approach its endpoints, meaning that this function will not have absolute minimum, but will have an absolute maximum. To find absolute maximum, we know that absolute extrema of a function on an open interval, if it exists, occurs at critical points. So we are going to find first derivative. So here we see that this function has three critical points. First is a stationary point at x is equal to 1 over 2, and we have 2 points, 2 zeros in denominator, x is equal to 0 and x is equal to 1. These are points where our function is not differentiable, but we are going to exclude this since we are only finding absolute extrema on open interval from 0 to 1. And second reason is that our function is undefined at these points. All right, so our absolute maximum is then occurring at point x is equal to 1 over 2, and it is equal to -4. Suppose that function f is continuous and has exactly one relative extremum on an interval, say at x0, then this relative extremum point is going to be absolute extremum point of that function on that interval. So part A, if function f has a relative minimum at x0, then f at x0 is the absolute minimum of function f on the interval. And if function f has a relative maximum at x0, then f at x0 is the absolute maximum of the function f on the interval. So to see why this is true, let's take a look at case of relative maximum. Let's assume that our continuous function has relative maximum at point x0. To obtain this maximum point, our function is increasing, then decreasing. And let's remind ourselves that only points where our function can change from being increasing to decreasing are critical points. So our function is increasing, it reaches its maximum point at x0, relative maximum point at x0, then it is decreasing. Now, to reach this height again and maybe surpass it, our function has to change its direction again. And this change in direction is going to produce another critical point, either a stationary point or maybe a corner point. Okay, meaning that if function has only one relative extrema on some interval, then this relative extrema is also absolute extrema point.
Let's find the absolute extrema, if any, of the following function on the open interval from 0 to plus infinity. So first we are going to study behavior of our function when it's approaching its endpoints of that interval. When x goes to plus infinity, our function is increasing without bounds. So we know from this, we know that our function will have no absolute maximum. When our function is approaching to its left endpoint from right, that limit is equal to 1, meaning that our function will have absolute minimum, an interval from 0 to plus infinity. So to find that absolute maximum value, we are going to then find critical points by finding first derivative. We find x is equal to 0 is a critical point, and x is equal to 2 is another critical point. And e to the power of this is always positive. All right, so inside of this open interval from 0 to plus infinity, the only critical point is x is equal to 2. So the only relative extrema point is at x is equal to 2. To see why this is relative extrema, we can indicate our critical points 0 and 2 and study the sign of f prime. When we substitute plus infinity, this is positive, positive, positive. These roots have even odd multiplicity, so the sign will alternate, meaning that our function is increasing, decreasing, then increasing. So at point 2, we have relative minimum. So x is equal to 2, which is relative minimum, is the only relative extrema of this function on that open interval, meaning that this relative minimum is going to be absolute maximum of our function. And the value function at point 2 is equal to e to the power of -4.